In this lecture, we'll be talking about distance metrics and hashing. And when we look at the larger class, across the 6 learning objectives, we can say in this set of lecture, we're going to focus on articulating math behind supervised and unsupervised techniques, particularly around unsupervised techniques. One of our future lectures is going to focus on clustering. In order to do clustering, we need to have some idea about the distance in elements, so the distance between elements in a particular cluster. So when we talk about articulating math here, in this lecture, we're focusing on how we can quantify similarity or distance between elements within a group. When we talk about extracting or building these clusters, we want to be able to say is points or nodes or elements that are within the same cluster should have high similarity or low distance, whereas 2 elements that are in different clusters should have low similarity or high distance. So that's where the focus on distance metrics will come from. Then we're going to talk about how we deal with similarity assessments or distance assessments when the data can be too large. How can we scale up to these kinds of questions? And I want to go into that not to make sure that you understand the specific implementation details of MinHashing and locality-sensitive hashing, but to give you a sense about how we can deal with data sets that are too large using hashing as a tool to help us reduce data set sizes. So how will we do that? So this week's learning objectives, there are 4 main ones. First, I'll talk about the possible distance metrics or similarity metrics that we will use in this class. As with centrality, there are many possible distance metrics that you might use. We'll focus on a few of them. So Jaccard similarity, Euclidean distance, and cosine distance will be the main ones. But there are also things like edit distance and other distance metrics that we'll touch on briefly. That's all going to be for informing us about clustering in the future. Then we'll talk about how we go from sets and set similarity for things that have well-defined sets to being able to extract sets from documents, specifically using shingling and the bag of words approach to featureize a document and then evaluate its similarity based on the methods that we describe in the distance metric section. Then we'll talk about 2 additional pieces for the dimensionality reduction case. So how do we deal with Jaccard similarity when the data sets could have many, many features, where the possible space of sets can be very large. As you see in the IMDb data set that we use in our exercises, there's a huge number of actors in this data set. So if you were to treat this as a data frame, you'd have a very large data frame, several 100,000 rows, several 100,000 columns that would be problematic to evaluate or store. But using MinHashing as a method for reducing dimensionality or reducing the number of columns in our data frame, we can still get good estimates for Jaccardian similarity or set-based similarity. So it'll be super useful for reducing the overall size of our data, but it doesn't help us understand or deal with problems where we want to evaluate the number of or identify the number of similar pairs across all of our data. So as we saw in the frequent item set mining case, these identification of pairs or similar pairs or pairs that co-occur together is a common problem and a problem that leads to scaling issues. But we can leverage hashing as a way to facilitate or deal with the scale problem by ensuring that we only ever have to compare pairs of elements that are more likely to be similar than 2 pairs of elements that are not. And the many pairs of elements that are unlikely to be similar at all, we never have to evaluate. We don't even have to look at those. And that will help us a lot when it comes to scale.
So first, let's talk about distance metrics. If we revisit the core motivation for the class, or one of the major questions we have, really what we're trying to do is make the web more useful and informative. And in the last module, in module 2, we talked about one way to do this is to group content on the web. Because as we saw, nodes that are similarly placed in a network, or nodes that are grouped closely together, are likely about the same topic when we're talking about graphs of web pages or graphs of information. And one of the examples we talked about is this idea of looking for or searching for documents about Jaguars. On the one hand, maybe we're talking about cars, maybe we're talking about the animal, maybe we're talking about software. And in fact, if we go to a place like Amazon and you do a search for Jaguar, you see that there's a variety of topics or a variety of kinds of products that come up, from books about or movies about Jaguar gods in the Yucatan to content or items about Jaguars, the king of the jungle, to the vehicle that we've talked about before. Now, when you click on one of these items, that then places you into one of these clusters in the network, and sources like Amazon are going to use this information to provide you with recommendations. What they want to do is give the customer a set of additional items that they may also want to buy based on whatever they're looking at now. So here, if you click on this book about Jaguar the car, you get all these other items that are recommended to you or about similar kinds of products that you may want to purchase. And all of these ideally are likely to come from this cluster around the Jaguar for the car topic, not from these other clusters about the animal or the software or Yucatan gods, right? Last time in Module 2, we talked about how we might do this, where if we identify a particular product of interest, so this Jaguar F-type complete story document or book, then we can use SimRank to identify what other nodes are you likely to show up on or land on if you start from this particular node in the graph. And this way you might find this Jaguar car's first gear, this button start center, or this other book about the complete book of Jaguar, every model. All of these products or items might be items that you're highly likely to land on if you first clicked on this Jaguar F-type. But this sort of begs an additional question. Well, what if we don't know exactly what product that the user's interested in? How do we then place, if somebody searches for Jaguar, where in this space they may be, and what other products might they be interested in, or how can we group this before we know what exactly the user's interested in? So this really becomes a question of identifying these groups, finding ways to group these items together. So one way we can do this is to recall SimRank. So SimRank says for a given source node, where are you likely to end up? So what this means is if you're here, if you start off at this product in the Jaguar case, maybe you're likely to end up at this node that has the highest SimRank, or this node that has the second highest SimRank value, or this node that has the second highest or the third highest SimRank value. So if you select a new node in this same group, as long as you're in this same cluster about Jaguars and cars, even if you click here, the expectation is you're still likely to show up, or you're still likely to go to one of these other three high SimRanked nodes, because these nodes with high SimRank are authoritative within this particular community about Jaguar the car. What's valuable here is that these two nodes, the two nodes that you might have clicked on, these two purple nodes, should have very similar SimRank vectors, that regardless of whether you start on the node on the left or the node on the top, you're still likely, or just as likely, to show up or end on one of these other three high SimRank nodes. So this lets us get a nice insight that if we look at two random nodes that are close together in the graph, we should expect that they're going to be similar to each other. And we would expect this with SimRank, that if we took these two nodes in the same cluster, they're likely to have very similar SimRank values. You can imagine this, or SimRank vectors, and you can imagine this graphically, like, well, you're still likely to show up, regardless of whether you click the left node or the right node, you're likely to show up or stay somewhere in that neighborhood. Whereas if you have the second cluster with one node very far away from the second node, the SimRank vectors for these two nodes are likely to be different, because if you start on either of these two nodes, you're likely to end up in very different places. So then we had this intuition that two nodes that are close together, two nodes that are in the same cluster, should be similar in some kind of way. So returning to our motivation about making the web more useful, when we talk about groups, we are talking about groups of things or clusters of things that should be similar in some way. But if we're able to leverage this similarity, then we can actually go the other way as well. So rather than knowing the groups beforehand and then inferring that objects in them are all similar, we can say we should be able to build these clusters by looking for similar entities. By being able to measure similarity between a bunch of different objects or a bunch of different entities, then we can figure out what these clusters really should be. So now we have a new question about if we're going to build clusters based on similar objects, how do we define similarity? Turns out this is really hard and dependent on your context. In the same kind of way that we talked about centrality last time, centrality is an overloaded kind of term. It can mean many different things based on your context, based on your kind of data. Turns out similarity is very similar in that regard. No pun intended there. So a couple of alternate definitions of similarity might be, we've already seen the adjacency matrix form that we've talked about throughout throughout module 2 about graphs, where here you might ask, well, nodes are similar if they have similar sets of neighbors. So if you and I share a common neighbor, then we ought to be similar. That's one way you could define similarity. Another way is if we look at this SimRank matrix, where the columns of this matrix are the SimRank vectors that we've talked about in module 2, then you can look at the similarity between these vectors and say, well, nodes that have the same SimRank vector or very closely related SimRank vectors should be in the same neighborhood. And you can imagine this geographically, that nodes with similar SimRank vectors would be suburbs of the same town or small towns around a large city. That they're all, like, these small towns may not be directly connected to each other, but they're all sharing if you started in one of these towns, you're all likely to end up in one of these large cities that are similar or authoritative in the particular area or neighborhood of these nodes. Or from the World Wide Web kind of perspective, similarity means something different if we're looking about web pages, where here similarity means pages about the same topic or generally about the same kind of thing. So if those are the different ways that we might operationalize similarity, or what similarity may mean in those different contexts, how can we measure that? Or how can we capture these different definitions of similarity? So if we go to the adjacency matrix method or representation, then similarity might be, or the way we might measure this is how similar are two vectors of edge weights. So if we have this binary adjacency matrix or an adjacency matrix that has edge weights between these nodes, we might ask, who or what sets of nodes have relatively similar sets of edge weights. Or we can look at this as a set question and say which nodes have the same sets of neighbors. And there's a particular distinction here that sets of neighbors are assuming that whether you are either a neighbor or you are not. That's the binary case. Whereas the former, this edge weight mechanism, we can say, am I closer to one neighbor than I am to somebody else? And are two nodes in the graph closer to one neighbor or closer to one node than they are to some other node? We might also define similarity as the similarity between two strings of words or two documents or two web pages, where we've operationalized these web pages into strings of words. Or we may ask about or try and measure similarity between two vectors of real numbers. So in the SimRank case, we have all these SimRank vectors for all these nodes. We're no longer looking at natural numbers or binary values. We're looking at real vectors or real numbers. So let's start with trying to understand or calculate or measure similarity within this SimRank metrics, because nicely this idea of similarity or distance between two vectors of real numbers should fit well with your recollection of geometry. Years ago when you were in high school, maybe you had talked about or learned about Euclidean distance. This is the standard kind of distance metric that you see in your geometry class, where you have 2 points and the distance between them is equal to the square root of the sum of the squares. We can flip this to a similarity metric by talking about the inverse of the distance. So you do 1 over the distance between these two objects, which gives us nicely as similarity goes to, or as the distance value goes to 0, similarity goes to infinity. So the most similar objects have the highest or almost infinite similarity. And the only time you'd see distance metrics of 0 or distance calculations for Euclidean distance of 0 is when two nodes or 2 points are exactly the same. So here we can then say, well, using Euclidean distance, we can measure the similarity or the inverted distance between two SimRank vectors. And that tells us that two nodes with very similar SimRank vectors, or two nodes whose SimRank vectors have very low distance, are likely to come from the same cluster or the same group of nodes in the graph. Now, a reasonable question here is, if Euclidean distance is great, it's the first one that that a lot of people learn in school. Why do we need more distance metrics? So remember, part of the objectives for this lecture are to be able to describe at least 3 such distance metrics. So Euclidean distance is 1. Why do we need more than that? Well, I encourage you to check out this review article by Pedro Domingos, where he talks about a few useful things to know about machine learning. One of the important ones is when we start talking about high dimensionality, or items that are in a high dimensional space, as are many things in the current web environment, things like Euclidean distance start to break down. That for really high dimensions, Euclidean distance is not a very good measure because things, like basically everything ends up being equivalently distant when you're talking about hundreds and thousands of dimensions. So let's talk about some other ways that we can operationalize similarity. So we've already talked about Euclidean distance. Let's try and ground this in a new context. So say we have an adjacency matrix. We want to understand the similarity between 2 vectors of edge weights. Now, maybe what we're trying to do is understand play styles or the kinds of language that announcers have talked about when they have described 2 football players. And say here 2 football players that have been in the league for a long period of time. So they've had lots of conversation. Announcers have said many things about them. There's lots of data about these 2 players. And let's say a new player comes on the field and he hasn't been around near as long as these other 2 players. And we want to understand, well, how similar is his play style, or how similar is his description, or the kinds of things that announcers say about him to the kinds of things or play styles about these other 2 players. The problem here is with Euclidean distance, because there's a lot of data for both of these 2 players on the right, these 2 highlighted players, in your general vector space, they're going to be very close, or they're going to be closer together because there's more opportunity. They're further away from the origin because they've been around longer. And a lot of their similarity is based not on whether they're actually similar, but based on the similar lengths of time that they've been in the league. And maybe what we care about really is, well, how similar are these 2 users, regardless of the length of time they've been in play. We want to understand something different rather than just this distance between 2 points. So one way to do this is with a new metric for similarity called cosine similarity, which measures, rather than the distance between these 2 points, the angular distance between these 2 vectors. So nicely, this new player and this older player in the top, can be similar even if they don't have a similar kind of longevity in the league. So the metric for this is nicely defined based on dot products and vector norms. So cosine similarity is a relatively straightforward thing to calculate based on linear algebra, and is nicely robust against differences in scales. So you may use this for comparing short documents to long documents, or these kinds of things. So also another nice property of cosine similarity is it's bounded between -1 and +1, meaning it's very easy to turn it into a distance metric by just doing 1 minus the cosine of the angle between these 2 vectors. So that gives us one way, or a different way, of evaluating similarity for this style, the adjacency matrix style, where we have potentially many vectors of edge weights between nodes. We can also define this alternatively if we look at the binary adjacency matrix and sets of neighbors. So now let's consider 2 nodes in this graph, C and E. They have neighbors. C is connected to A, E is connected to A, and to D. And we want to understand the distance between these 2 vectors. So the Euclidean distance is 1. That's the sum of the difference of this, the square root of the sum of the difference of squares. So 1 minus 1 is 0 for that top column, or for that top row, and then 0 minus 1 is -1. We square that so we get 1. So we just take the square root of that. Euclidean distance is 1. Cosine similarity is 0.7. That's actually pretty high. So we take 1 minus that, and we see cosine distance is about 0.29 or about 0.3. So this is quite a different kind of metric. But maybe we want to ask a different question. How many places do these vectors differ? That might be another way you might think of distance. And we can evaluate this using the exclusive OR bitwise operation. So then we just take what's the XOR between our C vector and our E vector. They only differ here in this one particular row. So in that way, you only have to flip one bit for C to become equal to E, or for these two vectors to be equal. Now, how many options or how many different times could they have been different? So that's the length of this vector. And now we have a new distance metric. So the distance between these two columns is 0.2 or 1/5, based on how many bits you might have to flip in order to make these two vectors the same. So this is a general distance metric called Hamming distance that comes up a lot when you have these binary sets or binary vectors. Alternatively, we can do a different kind of distance metric based on the proportion of shared neighbors. So of the neighbors that I have, how many, or of the neighbors that these two columns have, how many of them are shared between them. So here we can look at the intersection between these two neighbors. So we have really just A, both of them share the neighbor A, and we want to normalize that, so there's only one neighbor that's in common between them. We want to normalize that count by the number of possible neighbors that they could have. So then we take the union of all neighbors of columns C and E. So that's really A and D, because that's the only those are the only two nodes that are connected to the C and E. And then we can take the ratio between these two values, and we get 1/2. So we have a new distance metric, or rather a similarity metric called Jaccard similarity, which is exactly this, proportion of neighbors that are shared between two nodes in the graph, or any two sets of objects. So those are a number of different distance metrics you can use: Euclidean distance, Hamming distance, Jaccard similarity, cosine similarity, and the book has a number of other ones as well. But one of the things that I haven't talked about is evaluating similarity between two strings of words. So why is this a different thing? Well, first off, in the case for the adjacency matrix or the vector of simrank, or the matrix of simrank vectors, how we evaluate these, or similarity among these objects, can be relatively clear because we have numeric values here. That here for the adjacency matrix, the features are going to be other nodes, and either they're binary connections or sets of nodes that are neighbors, or they're simrank vectors that are all real numbers. For documents, we have to do something different because we can't just look at the numeric features of documents. We have to find some way to determine what the features of documents ought to be. So what might we do? Well, the obvious way is to look at the words or the letters in these documents and use those as a kind of feature. And in fact, the field of natural language processing has an extensive area of research based or focus on this question, where extracting features from text has its own area called vectorization, or its own process called vectorization. And how you do that can vary in a number of different ways. Probably the most common is to take a given document and extract all the words that are in that particular document, and take the union of all words in all of your documents, and then just count up the number of times those words appear in your different documents. So here we may have the document the cat sat. It has 3 different words. The cat sat in the hat. We have 6 different words there, and we can extract all the unique words from all of our documents and just count them up. Now we can then turn this into a matrix that we've seen already. This looks similar to a adjacency matrix that we may have seen, where we have nodes being documents and words. We actually have a nice bipartite graph structure here. So like I said, this is called the bag of words approach, and is extremely common in natural language processing. And then all we have to do to evaluate distance between two documents is say, well, we have this vector here of the number of times these different words occurred, and this vector here of the number of times these words occurred in this other document, and we can apply any distance metric that we want. But a difficulty comes in from needing to understand how many columns we might possibly have. Or if we're talking about natural language processing, trying to understand the language here, what words should be in our vocabulary. And this can be a complicated problem because words are essentially unbounded, and new words come into the language. What language you're talking about can change or alter what the column should be. So there's a lot of complexity here based on your context. So our book, Mining Massive Datasets, has a different approach to this, where we say, well, let's not care about the meaning of the word. Let's instead use runs of symbols. is ultimately maybe we have no real understanding what any of these words mean. So we can just look at runs of symbols or letters or numbers, these different grammatical symbols or syntactical symbols in language. And we specify, we'll look at runs of a particular length, because then we can know what all the possible combinations of this k length set of symbols could be. So if we know we have quote unquote words of 5 letters, what are all the different 5-letter combinations of the words in our alphabet? And that tells us how many columns that we can have. So the book calls this approach shingling, not this kind of shingling, but the idea or the intuition is this kind of shingling. We can extract these overlapping kinds of shingles of letters from, or runs of letters from our documents. So if we have the Wikipedia article for Amanda Gorman, then we set k size to be 9. Then it's actually relatively straightforward to take this text and create these shingles. These are essentially, you could think of these as all sorts of words in our document. And we see that this produces a bunch of these k-length shingles that overlap. And we can use these shingles as features in our similarity metrics. But we can go one better with this shingle metric. And that is based on an intuition that the likelihood, or rather the probability of seeing the run of letters and space the space s is not entirely clear what that probability is alone, but if we compare that to the probability of seeing a string of 4 x's, a string of 4 z's, and a y, we can be pretty confident that and the s is way more likely to appear in our words or in our document set than the string of 4 x's, 4 z's, and a y. This is a general sort of observation about language, that particular runs of letters are significantly more common than others. And if you think about this from the standpoint of a single letter in the alphabet, you might know this intuitively, that letters like R, S, and T are much more common than letters like Q, Z, and Y. This allows us to do a little implementation trick here, where we can take our K shingle, say here is K equals 9, so we have a shingle of 9 letters, or 9 symbols. This might be, if we're talking about ASCII characters, then we have this 9-byte representation. We can hash this into a number and then take use the modulo operator to compress this down to D bytes. So we take our hash, we mod it into D, and now we have a compressed version of this shingle. So here's an example of this in Python, where we take a hash of this string, mod 4, and hash of this other string, and modulo by 4, and we get 2 different values here. Now the importance, or the value that we get of this is we choose a value for D that's going to be smaller than our value of K, so we don't have to store or use as many bytes to store these representations of shingles. And because of our hashing mechanism, and then our taking the mod of this, any digit in this space of D is equally likely. So now we have a much more even representation, or a much more evenly distributed way of calculating or counting up these shingles, where we're no longer having to pay the penalty for indexing a number of shingles that are very unlikely to ever be used. But to pay for this, we have to accept that there's going to be some amount of error introduced into the system by these hash collisions, because now we've taken a space that's large and compressed it to a space that's small. So the pigeonhole principle would tell us that several of these strings that are different now have to hash to the same bucket, and we won't be able to differentiate between strings like and the I and the S in this particular instance. So as an example, we can take these 2 pages about Amanda Gorman, her Wikipedia page and her personal page, and put together a relatively straightforward function for shingling, download the content of these pages, parse them into text, and then apply this shingling and calculate Jaccard's similarity between these 2 articles. And we get some value, 0.023, so we can do this relatively easily and quickly. But there's a question here about, well, what does this Jaccard similarity really mean? Is this a high value? Is this a low value? Note that Jaccard similarity is bounded between 0 and 1, so this seems like a relatively low value. But what does this mean in the larger scale, or the larger scheme of things? And this is actually a really important point, because taking similarity between a single pair of objects is actually not hugely informative, and is difficult to interpret it without the additional context of similarity among other items. So really, the core value, or the straight values of a similarity metric, is maybe less important than how that value compares to other values. Now we can see this through the introduction of a new kind of structure. So we've already seen the adjacency matrix a number of times. We've seen modifications of this with the stochastic transition matrix and all these kinds of things. And for the adjacency matrix, we know that any cell in the matrix is a 1 if the ith and jth element are connected, and 0 otherwise. We can introduce a new version, or a new construct matrix, called the distance matrix, and define that separately and say that any element in this matrix, we redefine the ith jth element to be the shortest path, the distance or the length of the shortest path between a given node and any other node in the graph. And as long as the graph is connected, as long as there is a path from one node to any other node in the graph, then we can fill this matrix out. So for example, here we have the graph, this example graph we've seen a number of times. We note that the diagonal is all 0, because the shortest path from any node to itself is always 0. And then we can fill this out. The length from A to B is 1, because they're neighbors. Length from A to C is 2, because you have to traverse through node B. Length from A to D is 1, because they are neighbors again. And the length from A to E is 2, traversing through D. And we can fill this out for the whole matrix. And now we have a new set of values for which we can evaluate similarity. So why is this useful? What does this give us? What does this distance matrix allow us to do? Well, really, we can take any column in this matrix and sort them to find the most similar elements. So here, say we take node B, and we want to sort them to find that B is most similar to itself, second most similar to C, third most similar to A, and so on and so on. Now, for the distance matrix as constructed here, maybe this is relatively trivial, but you'll note this should give you, or start to give you some hints for how you might approach assignment 3, where we want to build some matrix that's similar to this and evaluate or rank objects based on their similarity or based on their distance. Now, I've provided a distance matrix using the shortest path construct. You could easily do the simrank construct as well. So a distance matrix that's made up of the columns, or whose columns are made up of simrank vectors, is actually, I suppose, more of a similarity matrix than it is a distance matrix. You could invert them to go from similarity to distance matrices, as one might expect. So there are many different ways that you can operationalize or construct a distance matrix. These two methods work pretty well, or work nicely for graph constructs, where you can easily calculate path lengths, or you can evaluate eigenvalues on an adjacency matrix, and so on. But you can definitely do other things as well. So you can calculate the distance between two elements using Euclidean distance, or Hamming distance, or cosine similarity, or Jaccard similarity, or many others, and fill out this matrix in a different kind of way. Similarly structured, but very different kind of information that you might extract. So for instance, if we have this example, we have this adjacency matrix, we can evaluate things like Euclidean distance on this matrix. It's a pairwise square matrix where we have distances between all pairs. And you can see by reading this off that node A is most similar to node E in the graph based on Euclidean distance. And in fact, cosine distance is similar. We see some differences between Euclidean and cosine distance, especially with respect to node B, where in Euclidean distance we see that node B is pretty close to C and D, but in cosine distance, node B is actually just as far away from C and D as it is from E and A. And we have Hamming distance and Jaccard distance and simrank distance as well, which we can see there's slight variations across all these different distance matrices. And in fact, the scikit-learn package for Python has a pairwise distance function, has many different options for which distance metric you want to use based on what your particular context is or what your particular needs are. So why do these matter, right? So I've already showed you or talked about taking one of these one column from these distance matrices and use that to do ranking. But in fact, you can do this from a larger, more general context and use these distance matrices to evaluate clustering algorithms or build clusterings. So we talked about when we defined what clustering is as a task, it's trying to group nodes into groups of similar objects, where similarity may be defined in a number of different ways. You could also do this or use these distance matrices for recommendation. So this is where we'll go for the rest of this module, where a person buys a particular product. We want to be able to identify similar products, and we want to recommend those similar products to the user. And it's not really practical to do this every time somebody identifies or somebody clicks on a product. Ideally, we want to build this ranking of similar products beforehand. So when somebody selects a product, we can very quickly give them what is the most similar product or what's a set of similar recommendations for them. So what this should tell you is the distance matrix construct is useful, but there is issue with their applications. Primarily that they are large. Reach back to your complexity class or your complexity days. You see this matrix is order n squared in terms of size based on the number of objects that you want to evaluate for which you want to evaluate similarity. Now, in general, maybe this might not look like a big deal to you because the adjacency matrix is similarly structured. It's also n squared. But the big difference here is that the distance matrix is large, but it's also generally a dense matrix. So we can classify or really distinguish between dense and sparse matrices, where sparse matrices are matrices that are primarily zero in many, many places and non-zero in very few places. The adjacency matrix in most real-world networks satisfies this because the vast majority of singular elements or single nodes in like a network are not connected to a huge number of nodes. They're only connected to a handful. And then we only have to store what those connections are, and we don't have to store the entire graph or the entire matrix. For distance matrices, on the other hand, these nodes have very few zero elements. In fact, most elements in the matrix are non-zero. In fact, with the distance matrix in particular, one of the examples we showed is the distance matrix is only zero, or cells in this matrix are only zero along the diagonal. In fact, the vast majority of them are non-zero. So this is problematic because when we look at something like Amazon, we have 12,000 or 12 million products that we want to identify and then provide rankings for, similarity rankings for. And we're talking about 12 million elements. We have to do 12 million choose 2 to get all pairs. So we're talking about 144 times 10 to the 12th pairs. We assume that we're using 64-bit floating point numbers, so we're talking about 10 to the 15th bytes, or approximately 1 petabyte of information just to store this distance matrix in memory, which is either going to be an exceedingly expensive machine to store this in RAM, or it's just not tractable. And this problem becomes even worse when we talk about social media networks or large-scale networks like the web. We have millions, hundreds of millions to billions of nodes, and storing something like a distance matrix just for Reddit, which is a relatively small social network compared to Facebook or Twitter, could take up to 1 exabyte just for a random back of the envelope kind of calculation. So this is clearly not something that we can do tractably. We can't store the entire similarity matrix or distance matrix for these large data sets. So when we go back to our core motivation, remember the goal here is to find groups of highly similar pairs. But since we can't store all pairs of nodes, we have to do something different, or we have to find some ways to be clever about where we want to evaluate similarity. The web is a vast place, and most things of interest on the web have many features, and there are many elements of things that we want to analyze or that we want to understand. So when we talk about trying to evaluate similarity, we can't do this for all pairs for the reasons that I mentioned, but we also have the additional problem of documents that have, or elements in our data set can have, many columns or many features of interest. So these become really high dimensional data elements. The problems that this leads to, so we've already talked about how we can't fit the whole distance matrix in main memory. This is problematic if we want to provide rankings of similar items for recommendation. For this other case where we have high dimensionality, we've already talked about how high dimensional spaces introduce problems for distance metrics. In fact, if you're familiar with word embeddings or network embeddings or image embeddings, part of the whole goal there is to generate low dimensional dense embeddings to avoid this issue of high dimensional spaces. But the problem is doubly worse because here, if we want to hold the whole feature matrix in memory, we have potentially many documents or many elements, all the nodes in our graph or all the products that Amazon wants to sell, and we can have many features as well. So either all of their features, or if you were talking about rows of images or a data set of images, it could be all pixels in the image. So just storing the matrix that characterizes all of our data could itself be very large, let alone the similarity matrix comparing all of our elements. So we need to address these two problems. So we'll address this one about the documents having high dimensionality. Here we'll talk about an example of using MinHashing, which allows us to compress these feature spaces into a smaller dimensional space. That works well when we're talking about data sets of sets. And the key insight here is these compressed feature spaces maintain or preserve similarity among two objects. So for these small signatures that are going to be hopefully much smaller than the full feature vector, that the similarity between these short signatures is equivalent or very similar to the similarity in the full feature space. Like I said, this is meant for contexts where we have sets and we want to evaluate Jaccard similarity. There are other methods for other distance metrics as well, which we'll talk about. Now, MinHashes let us evaluate similarity in low dimensional spaces, which is nice. Locality-sensitive hashing allows us to deal with the all pairs problem. So rather than trying to fill out the full similarity matrix or the full distance matrix for all n-squared pairs, we only want to evaluate similarity for some candidate set, some set of pairs where the pairs only matter if, or we only evaluate similarity among a pair if we think it's actually similar, if its similarity is above some threshold, which lets us throw out a whole lot of samples or a whole lot of elements that are unlikely to be similar. And this should remind you of some of the discussions we had around SimRank and some of these and the PageRank algorithm, where with SimRank, one of the optimizations was there's actually no need to visit many nodes in a graph because many nodes are far away and we don't care about those. So here, maybe there's not reason to evaluate similarity among many of the pairs of elements in our data set because the vast majority of them we would expect to be not similar and not be useful to us. So let's first deal with or talk about MinHashing. So what I want to do is give you some outline for how we use MinHashing to find similar documents in this short space. So we have a set of documents which we've shingled up, and we've already talked about shingling. And what we want to do is represent these documents using a matrix, where all the columns in our matrix are Boolean vectors telling us which shingles exist in this particular document. And what we want to do is find similar documents, or find pairs of documents that are similar, while computing only small signatures. We don't want to have to store a full set of features for all of the elements in our set. So we don't want to have to deal with storing the full set of shingles for everything, because that might be too memory intensive. And we want to make sure that the similarity between two documents should be equal to the similarity between the signatures, these short signatures of these two documents. So given this goal, we can have a relatively naive approach where we generate these signatures for all documents. These signatures should be small. And then we examine pairs of signatures to find similar documents and make some constraint here that similarity between two document signatures must be related to or somehow proportional to the similarity of the two documents in the full vector space. And then we have this option to actually go through and evaluate all of our signatures to see which documents are actually really similar. Because remember when we talked about the hashing trick with shingling, when we do this kind of compression, we introduce opportunity for error into the system. Some things to keep in mind. First off, comparing all pairs is problematic for all the reasons that we mentioned, with the distance matrix being dense and too large. And as I mentioned with the noise aspect, because we're dealing with these compressed smaller signatures, we've introduced opportunity to have false negatives and false positives. So a false negative here is that two documents are similar, but we're not actually seeing them as similar. And a false positive here are two documents are similar, or rather two documents are not similar, and we have said that they should be checked. They're a candidate pair when really they actually aren't similar. Remember, we have this constraint. One of the big deals here that we want to maintain is that these signatures should tell us something about the similarity of these two documents, even in this smaller space. So from some notation perspective going forward, when we talk about columns in a matrix, really what we're talking about are documents. So you'll see this come up in a second. So the key idea behind min-hashing is to hash each column or each document to this small signature, such that the hash is small. We want this signature to fit easily in RAM when we look at all of our documents. And we want to make sure that the similarity between two documents is the same or very close to the similarity of the signatures generated by this hashing mechanism. And the goal here is to find a hash function that satisfies these constraints. First, that if the similarity between two documents is high, then two documents should hash to the same bucket or the same value. And if the similarity between two documents is low, then we should have a high probability that the hash of these two documents are not the same. Though note that we're talking probabilistically, that doesn't mean that has to happen. So here's what we expect to see. So if we have a set of three documents, we have some constraint that document 1 and document 3 are very similar to each other, much more similar to each other than they are to document 2. We have some hash table that we can use to hash these documents into a compressed space. D1 and D3, these two documents, should hash to the same cell in our hash table since they are similar. And document 2 should hash to a very different cell or some other cell because it's very dissimilar from these other two documents. And we use the fact that there's a collision here in this hash table to tell us that D1 and D3 are a similar pair or a candidate pair for similarity evaluation. So we have these constraints. Note that what the min-hash actually looks like, or what this mechanism for hashing actually looks like, depends on how we're actually evaluating similarity. Not every single distance metric that you can imagine has a suitable function that does this. What we'll do here with min-hashing, min-hashing is suitable explicitly for Jaccard similarity. We actually will show that min-hashing, or the similarity between two documents min-hashes, is equivalent to the Jaccard similarity between those two documents. There are three things we need to do here. First is we have our matrix, our Boolean matrix, where columns represent documents, rows represent shingles in the document, and cells in the matrix tell us whether that shingle is present in that document. We introduce a random permutation pi that allows us to say, or reorder the rows of this matrix. And we define this hash function to be the index of the first non-zero element in this permuted order in the column for this particular document. And we denote this hash function as the min of C. And what we want to do here is take many different permutations to create a sort of sample across the possible permutations of this hash function. And we'll do this k times. We'll do k different permutations, and expect that the value that we choose for k is going to be much smaller than the total number of features that we may have. So we want to create a min hash for a given document that takes all possible shingles that we could have and compresses this into a k element signature. So what does this look like? Let's walk through an example about what we're doing here. So we have our input matrix. which has columns for documents and rows for shingles. And we have this permutation vector, which allows us to reorder the rows of this document, or the rows of this document matrix. And what we want to do with minhash is look for the first element in this permuted order that is non-zero. This is our min function. So here, the first row in our permutation matrix is moved down to the third to the bottom row. And we see that for columns 2 and 4, we introduce a 1, or we see a 1 there. So that tells us in our signature matrix, this is where we are recording the output of these permutations, or of this min function. We say, well, the first, in our permuted order, the first row that we identified as having a non-zero element is 1. We put that in the columns for the second and fourth documents. Then we go to the second row in our permuted order, and we see that, well, now we have a 1 in the first document and the third document. So we put a 2 in our signature matrix here. Now that we've filled out our signature matrix for this first permutation, we have filled out the signature row for this first permutation. We do this for a second permutation. We go to the first row. Again, we see that in documents 2 and 4, our first row in our permuted order has a non-zero element, so we put a 1 there. We go to our second row, and we see that document 1 has a 1 or a non-zero element there. So we say this happened in our second row of our permuted order. But note that we don't have a non-zero element for document 3 yet, so we keep going. We see it doesn't occur, and we don't have a non-zero element for document 3 in row 3 either. So we have to go to row 4 in our permuted space. Now we have a new signature row in our signature matrix. And we do this again. You can do this for many permutations to get many samples of this min function. And you can re-index these different ways as long as you're consistent. So whether you're doing row indices in your permutations or some other indexing approach, as long as you're consistent, that's key. And the claim here is that similarity among columns of the signature matrix should equal similarity among columns of the input matrix. So we do this, or this claim is called the MinHash property. And what we say here is that the probability of two documents hashing to the same value should be equal to the similarity between, or the Jaccard similarity between those two documents. So let's go through the proof for why this is. We let C be some document, which is a collection of shingles. Y is a particular shingle in this document. Then we can say that the probability of the permuted row of Y being equal to that first time where we see a 1 or a non-zero element in our permuted row is uniformly distributed over all possible rows of our document matrix. Recall that the min function, as we've defined it, is the first row in our permutation that's a non-zero element. So now let's specify Y is a particular shingle such that the permutation of row Y is the first row in our permuted document column that is non-zero. But rather than the document column being a single document, we'll take the union of shingles in two documents, C1 and C2. So that means one of two things has happened here. Either the 1 in this column comes from document 1, or the 1 in this column comes from document 2. Because the only way that we'd have a 1 in this column is if there was a 1 in one of those two documents. The probability that Y came from both C1 and C2 is equal to the probability that Y came from the intersection of these two documents. So we can rewrite this and say the probability of the first non-zero element in our permutation of the first document being in the same place as the first non-zero element in the second document is the likelihood or the probability of those two things happening at the same time over the probability of the union of these two documents. We can rewrite this as the number of times where there's an intersection, or the number of common points between, or common shingles between these two documents, over the size of all shingles in these documents, which is exactly the Jaccard similarity that we were going for. So now that we have this property, we can repeatedly sample this probability function using k different hash functions, that is k different permutations. And the similarity of the two signatures can be defined as the number of cells in these signatures in which they agree. Essentially, you have this sampling structure where we would expect the proportion of agreement in these two signatures to be equivalent to the Jaccard similarity of these two documents. So what does this look like if we have a signature matrix for these two documents and these three minhash signatures? In this first row, they are not equal. In this middle row, they are equal. In this bottom row, they are not equal. So we have a similarity, or an estimated similarity of these two documents as being 1/3. So now we can actually show what this looks like through some examples. We show for the similarity between the two columns, actual Jaccard similarity is 0.75 or 3/4, and the similarity in the signature matrix is 2/3. So it's close to, or a good estimate of, the similarity between the first document and the third document. We can go through and see what this looks like. So comparing these two documents in the input matrix, since we're doing Jaccard similarity, we don't care about non-zero element, or we don't care about elements that are zero in both documents. So we only care about these 4 rows that have a 1 in one of the cells, and only one of them is different. So this says that the first and second to last and last rows are the same, and that only that second row is different. So in 3/4 of the time, we have the same neighbors, or we have the same shingles. So that tells us the Jaccard similarity here is 0.75. We go look at the signature matrix, and we see in these 3 rows, we want to look at all the rows, and we find that they're only different in 1 row. So that tells us that 2/3 of the time, or 2/3 of these of the rows in this signature matrix, these two elements, or these two documents, are the same, meaning their similarity in the signature matrix is 2/3. So another, again, an estimate of the Jaccard similarity. And we see the same thing if we look at documents 2 and 4 that share some overlap, whereas documents 1 and 2 have 0 overlap, both in Jaccard similarity and in their signature, and documents 3 and 4 have similarly 0 similarity in their Jaccard similarity or in the signature. We've shown that with a small value of k that's much lower than the actual size of the number of shingles that we might have, we have maintained, or we have a mechanism for evaluating similarity between two documents with these small signatures. We've compressed these feature vectors into these small k-sized signatures, which is the goal that we had for MinHashing. All right, so let's wrap up this discussion by talking about locality-sensitive hashing. So recall the goal here is to deal with this problem where we can't store the entire distance matrix in main memory. So what we want to do is only have to look at documents or pairs of documents where they're similar of at least some, or their similarities at least above some threshold. Crucially, we want to avoid having to evaluate similarity for all pairs of things. So for locality-sensitive hashing, the idea is to create some new function that tells us whether these two documents should be evaluated as a candidate pair. They are a candidate for being similar. So this function gives us a 1 if we should evaluate these two, or if there's a high likelihood that these two documents are similar, and a 0 otherwise. So for min-hashing, what we want to do is hash the columns of our signature matrix into a bunch of different buckets, such that if these two columns of our signature matrix are above some threshold of similarity, that they end up in the same bucket of these different hashes. So one of the things you'll note here is that hash collisions, or collisions in the hash table, can tell us a lot about what's going on with the underlying data. So for min-hashing, what we want to do is pick some similarity threshold S. Remember, this is Jaccard similarity, so it's between 0 and 1. And since we're using min-hashing, we know that if 2 columns of X, so two columns of this signature matrix M, document X and document Y, if their signatures agree on at least S fraction of their rows, that means that they are likely to be at least S similar. And agreement in these hash results tell us something about the similarity of these documents. So the main idea behind locality-sensitive hashing here is that by hashing the columns of these signature matrices several times, we hope or try and ensure that only similar columns are likely to end up in the same bucket of these hashes. So only columns that are above our similarity threshold result in hash collisions, at least probabilistically. Hopefully, by over the course of many of these or several of these hash functions, we get some high probability that this happens, or this hash collision happens at least once. As a result, so any time we have a hash collision or two documents that end up in the same bucket, we call this a candidate pair and say that this is a thing that could be similar, so we have to go check this. So what does this look like? We have our signature matrix M. So remember, this is the minhash matrix we just talked about, where one column is a signature of our document. And we want to divide this signature matrix into a bunch of small collections of bands, where each band consists of R rows. Now, note that means that the product of B and R must equal the number of or equal the K value from our minhash algorithm. So if you set R to be 1, then the number of bands equals exactly the K value from minhash. Then for each band in this signature matrix, we hash that portion of the rows to some hash table with many buckets, or with a different version of K set of buckets. And at any point in time where these two bands, or the bands of two documents, end up in the same bucket, that gives us a candidate pair that we want to evaluate. And we want to tune the values of B and R such that we catch a lot of pairs that are similar, but very few false positive, very few pairs that are not similar. So we can evaluate or show this graphically. So say we have 7 different documents in our signature matrix here. And this signature matrix has been divided up into B bands of R rows each. And if we apply some hash function to this first document, it goes into one of these buckets. The second document goes into a different bucket. Third document goes into a different bucket. Fourth document goes into a different bucket. Now when we hash this fifth document, it goes into the same bucket as the second document. This sixth document goes into the same bucket as the second, and this last document goes into the same bucket as the fourth. Now we know or can specify that these 3 collisions tell us that these 2 documents, or these pair of documents, are probably similar. We're not guaranteed that they are, but there's at least a higher likelihood that they are similar. We call this our candidate pair. And we say that these 2 columns, or these 2 documents, 6 and 7, they map to different pairs, so we don't know anything about their similarity other than for this particular case, or for this particular row, or set of, or band, these 2 things are not similar. So as I mentioned, then you tune the number of bands, which specifies the resulting number of R rows per band to get to the number of, or the length of our signature from minhash. And by looking for, or only having to evaluate documents that hash to the same bucket for these B bands, we can reduce the amount of pairs that we have to check by a pretty sizable margin. So we don't have to check all the n-squared pairs. We check only those that end up in the same bucket, which should give you some insight into at least the idea behind locality-sensitive hashing. And we'll talk more about the specifics of this implementation next week when we talk about dimensionality reduction in Module 4. But just the major takeaway here is, by applying this particular hashing structure and only caring about times, or only caring about pairs that end up in a hash collision for one of the bands that we've hashed in using this LSH mechanism, that we only then have to evaluate similarity among these candidates and not have to evaluate the similarity among all pairs. Now again, there's some opportunity for errors here with both false positives and false negatives, but in general, this penalty is worth the cost savings we get in memory. That wraps things up for this lecture. The learning objectives here, remember, give examples of at least three distance matrices or three distance metrics. You should be able to talk about Jaccard similarity or Euclidean distance or cosine similarity or Hamming distance, etc. You should have some sense of what shingling is and why it's useful for the web in particular, and converting web pages into the sets that we've talked about when we've talked about graphs. You should be able to describe why minhashes provide an estimate for Jaccard similarity. And lastly, you should be able to at least get or describe the intuition behind locality-sensitive hashing, namely that by relying on hash collisions, we can identify possible documents that are likely to be similar or more likely to be similar than not.